All right. Hi, everybody. My name is Varun. Usually I don't show up to the Thursday meetings, but this week, surprise, you guys get to have me instead of your normal instructors. So I'll introduce myself real quick. I'm a fourth-year electrical engineering student. I normally teach Monday trainings. I'm on BattleBots Hockey, and I'm the bot lead there, and I also work on electrical stuff. I used to be on Robo Racing Electrical. And so today I'm going to talk to you guys about some design principles that will help you understand the design process better, and then the timeline and what are the steps that you need to take when you guys are making your own circuit boards. So last week, it was split up in electrical and firmware training. In electrical, you covered laying out your circuit boards. In firmware training, we talked about some communications, and specifically we did a lab on I²C. And this week, we're going to talk about the design decisions that you would make when you're building a circuit board, how to choose those requirements for your circuit board, and then overall planning for your board design. So first, let's talk about what is the design process. Here you could see like a flow chart. We start with the requirements, trying to understand what the board is supposed to do. And here we want to do, after that, a block diagram showing all the different subsystems in your circuit. And we can prototype at the same time to make sure that those subsystems are logical and possible to do. And once you have an idea of what you want to do there, you should finalize the components that you want to use based on the results of your block diagram and your prototyping. And here you can spec some of the important components that you would need, like, for example, a microcontroller, any particularly large or important ICs, so on and so forth. And then move on to drawing your schematic in Eagle. And this first beginning part is a combination of collaboration of firmware training or firmware group, electrical hardware group, and maybe even your mechanical and software teams as well. After the schematic is finalized, they'll split off, and then the firmware people will be focusing on the firmware design, writing the code and testing for that, whereas the electrical hardware people might be doing their circuit board layout, having a design review, producing the circuit boards, and then finally fully testing. So there's kind of two parallel structures of what the firmware team would be doing and what the electrical team would be doing. And of course, at the design review, you're going to get some feedback from other people. How's the board going to work? Are there any things that could be wrong with it? And based on that, you might need to go back to a previous step in this process just so that you can resolve any issues that might have come up in that step. So now we'll talk about requirements and constraints. First thing you want to do is you want to have a very well-defined idea of what the board needs to do. It shouldn't really be in a gray area, any of the things that the board needs to do. And so you're going to need to communicate with the other people on the electrical sub-team for your group. You're going to need to communicate if your board needs to communicate with ROS or something. You're going to have to talk to your software team. If it needs to physically mount in a place, you might need to talk to your mechanical team. But it's important that you understand in a well-defined way and systematic way what the board's supposed to do. For your block diagram, you're going to need to consider inputs and outputs for your board. Especially, you need to consider the communication, what sort of data flows into the board and what sort of data comes out of the board. The data could be analog signals or digital signals. Either of those two things would be considered data flow. And then lastly, you need to consider power, because the board needs energy in order to turn on, and the board might supply energy to another component. For example, a motor. The board could be connected to a motor or another circuit board, so it needs to be having inputs and outputs of power. And whenever you're designing, there's three things that you need to keep track of. That's size, weight, and power. We abbreviate it to SWAP. You might also consider cost as well. And generally, you want to minimize those categories. Cost, we actually tend not to minimize cost too much in RoboJackets because the number of, unless we're making something that's prohibitively expensive, the quantities that we make boards at means that we don't really need to optimize for cost, because they're going to be overall not too expensive. So now to talk about inputs and outputs, let's talk about the power system first. What is giving the board energy? You could have the main battery of your robot connected to this board. You could have a separate battery connected to the board. You could have a power regulator in between the battery and the circuitry on your circuit board. There are a lot of different options here. And you can basically select this by thinking about how much power does each component on the board use. Your circuit could even be comprised of a bunch of different subcircuits, and each of them might need their own power system to be considered. So you can kind of choose this based on what voltage and what voltage is required and what current is required. And after deciding those two, you can decide what kind of power regulation or power source you might need. And communications. There's going to be data flow, of course, because our boards have to do some sort of processing usually. And so we can think about what information does the board need to do its job. For example, it might ask for a command from another board. Let's say it could ask for a command from a PC and then use that command to perform some action. Or it could be receiving data from a sensor. That's more information that the board needs. And now once you think about what information you need, you can think about how does that information arrive. And this is what sort of communication protocols and data formats you're going to get. Are you going to get 1 byte at a time? Are you going to get 2 bytes at a time? Are they coming in I2C, SPI, UART, so on and so forth? And lastly, at the very lowest level, you'll have to consider the voltage of those communication signals. That's the physical layer. And here you can say, oh, we need our 5-volt board needs to talk to a 3.3 volt device. How do we do that? There are circuits that you'll need in between. And all of these considerations are going to drive what sort of circuits are going to be needed on the circuit board. So often in RoboJackets, we have a microcontroller on our circuit boards. So it's important to consider a microcontroller isn't always necessary, but necessary in many cases. So why would you want to use a microcontroller? A lot of times it's useful for decoding any complicated digital protocols. For example, if you have to take some data that comes from SPI and you have to put it out in a different digital format, it's often really convenient to do that with a microcontroller. If you need to perform any sort of calculations or processing, for example, if you need to do some math once you've got some sensor data, then a microcontroller would certainly be able to do that. And in general, if your board function has to change a lot, it's a lot easier to reprogram something because, code is free. It's easier to reprogram something than it is to disassemble a circuit and reassemble it in a new way if you have a hardware-based solution to the problem. So once you know, yes, I do need to use a microcontroller, or no, I don't. If you did need to use a microcontroller, you have to consider what are the specs of that microcontroller. What sort of features do we need on it? And as you may recall from firmware training, the microcontroller is got a CPU and it has many peripherals connected to that CPU. So what peripherals might you need? You might need timers. You might need a PWM output. You might need any communication protocols such as I2C or SPI. So your block diagram might actually influence the choice of microcontroller here because you'll realize, oh, I have this many devices that need to communicate over a particular communication protocol, which might motivate the microcontroller which has more buses of that peripheral. So in addition to that, you might want to also consider just how well that processor performs. So you can look at the frequency of your processor's CPU. You might also want to look at something called a FPU, or a floating point unit. And a floating point unit is a very useful part of your microcontroller when you have to do any complicated math. For example, any math which is used for feedback control, or math that's used for digital signal processing, often requires you to do math with decimals. You can't just get away with using only integers. And microcontrollers that have a FPU will be able to do decimal calculations a lot more efficiently than ones that don't. However, if you are considering that maybe a microcontroller isn't necessary, you can always try to find a specific integrated circuit that does the job that you want. And I would highly recommend, if you ever start a new project, just do some Googling and see if you can find an IC which does the exact function that you need. You'll find it more often than not. You might want to look for a circuit made out of discrete digital components or analog components. And in many simple circuits, you can just draw it out using the skills that you've learned from your low-level ECE classes 2040, 2020, and find a solution to your problem which doesn't need a microcontroller. And lastly, if you have any complicated digital circuits, you may want to look into using a field programmable gate array, or FPGA. And FPGAs, they allow you to kind of synthesize different sorts of digital circuits using code. So you can program a chip to act as another type of digital circuit, which has some of the benefits of a microcontroller in terms of reprogrammability, and it has some benefits associated with a hardware circuit, such as the efficiency and the high speed. They're quite involved topics, so you have to have a little bit of that technical background in order to go into FPGA. So one common component, we see it on almost every robot, I would say actually every robot, is a motor. So electrical team definitely needs to have some input in choosing the motor, and they're going to need to collaborate with the mechanical team to pick that motor. So the way that you could choose motor, you have to look at the speed, torque, current, and voltage, as well as the efficiency. And in the next slide, we're going to discuss some different types of motors and what each of them is successful at. But in addition to the motor, you're also going to need to select a motor controller circuit, which is going to directly follow from your motor specs. Different types of motors are going to require different types of motor controllers, and they will all have different ratings for voltage, current, communication, so on and so forth. Usually they're going to be given in terms of a continuous and a peak current. The continuous current and peak current, it's kind of by the name, you can tell what they mean, but you should make sure that your continuous current limit is met by the motor, so that way, if the motor doesn't draw too much current, your motor controller isn't going to heat up, get too hot, and possibly break. And if your motor controller has some current limiting software, you actually have, we call it fudge factor, but you have the ability to let your motor have the potential to draw more current than the motor controller can handle, because the motor controller is intelligent and it'll know I'm not going to put out so much current that it'll break myself. So now here, like I mentioned earlier, there's many different types of motors. In fact, we have 4 different types of motors that we commonly use in RoboJackets. And these are brushed motors that are very simple to control, because if you just apply a DC voltage to the red and black wires, the motor will spin, and it even spins at the speed proportional to the voltage. So it's very easy to pick a voltage which just cause the motor to spin how you want. And following that, we have brushless motors, which rather than using a constant DC voltage, you have to apply a sinusoid voltage pattern to them. And so this makes the control of a brushless motor much more complicated than it does for a brushed motor. However, you get the benefit of very efficient, because unlike a brushed motors, they have brushes as per the name, and the brushes generate friction, they generate heat, and they cause you to lose energy. Brushless motors have almost no touching components inside them, so there's really no friction. They're very smooth and thus high efficiency. You may want, if you have particular position control requirements, if you need to control the speed of something, brushed and brushless motors are very effective. If you need to control the position of something, the stepper or servo motors might be a more accurate choice. For a stepper motor, you can cause it to move forward in steps by alternating voltage pulses across each of the 2 internal coils. And the benefits of a stepper motor is that you get very high torque and very high holding power. You can energize one coil and then the stepper motor will stay there, it'll never move. Servos, on the other hand, you can give them a digital input signal of some sort of communication protocol, and that digital input signal gets translated into a precise position or velocity command, and the servo has an internal control mechanism which will cause it to rotate to that position or velocity command. And it's worth noting that if you add some sort of sensor to a brushed or a brushless motor, and then you add a feedback control algorithm such as a PID controller, you can turn either one of those two motors into a servo motor. Sometimes, though, it's just easier to buy the thing rather than having to make it yourself. So if you can find something that performs to your spec and is within your cost budget, then it's usually better to buy than to DIY. So we always know that robots, they need to move, so they need to have motors. Robots also need to sense their environment, so they need sensors. And sensors are usually where you're going to want to talk to your software team, because your software team might think, oh, these are the sort of algorithms we're going to need to run, and we need this information in order to do those algorithms. And so given those requirements, you on the electrical team will need to be able to integrate these sensors into a platform which they can write code for. So here you want to consider the dynamic range, which is the minimum and maximum measurements of your sensor, the accuracy, the sample rate, which is how fast you can measure from that sensor, and then the communication protocol. The communication protocol, you should choose it so that it's more convenient for your circuit board design. If you choose one that you don't really use or don't have experience with, you're going to have a harder time doing it in the end. And you should choose one that your microcontroller is capable of easily supporting. So it's important to do some calculations. You can prove a lot of things that could or could not go wrong with your circuit board using math. A lot of times we do hand calculations. You might need hand calculations in order to understand how much information flow is in your system, whether your CPU can handle it, whether your communication bus will be able to handle it. And you can also use hand calculations, circuit analysis, so you understand what the currents and voltages are flowing in every one of your components. And lastly, you'll definitely want to do a hand calculation or use an Excel sheet to keep track of how much power your board is theoretically consuming. But these are all very effective in simple cases. For complicated systems, you may want to try to use a simulation software like Multisim for some complicated systems that you might need to simulate. And as a bit of warning, Multisim is very effective when you're trying to simulate an analog circuit. Circuits which require digital stuff and you have to write code for them, Multisim is not really going to be effective for simulating something which runs firmware, essentially. And so for that, your best bet is to do some prototyping, which in that case, buy some of the components that you're thinking of using or thinking of testing out, put them on a breadboard or put them on a test circuit board, and see if they work. Prototyping, there's no substitute for prototyping. Simulation comes close, but prototyping is still the best. So once you have a good idea of what you want to do in the end, you want to choose all the different subcircuits or subsystems in your circuit design and think about how each subcircuit should solve one different aspect of your functional requirement. You could have, if you have a particular IC that you need to use, you're going to need to make a subcircuit which supports that IC. You might need a different circuit to handle your communications physical layer. You might need a circuit for your power regulation. You'll have some number of these based on how many ever different things that your circuit needs to do. And it's important to keep track of what each subcircuit does and keep track of how it's related to the other subcircuits in your circuit board. So I talked a lot about hardware. Simultaneous is the firmware development. So microcontroller, this is a 4-step process. You start by setting up your microcontroller, making sure that all the features that you need are going to work, make sure that your RAM and flash, the program is going in the right place. You can program it. You can do your PWM at your desired frequency and desired duty cycle, so on and so forth. Test your communications and just set these up. And frameworks like Arduino make this really easy. You'll do it without even noticing. Then you want to write device drivers. So for every chip on your board that you might need to communicate with, you're going to need to write a driver that makes it very easy to communicate with that. Some of you may remember from firmware training, we had to set some bits directly in order to make some actions happen on the IMU. But an alternative to that would have been to write nice calls in methods that wrap around that bit setting action. And in doing so, you make it easier for everyone to write code because they don't have to go back to the datasheet. Oh, check, I needed to set bit number 3. Instead, they just have a method which automatically does it. So once the hardware side is out of the way, you can work on the code for each individual subsystem. And those subsystems might integrate multiple different devices. For example, your motor subsystem, your motor control subsystem might need a motor driver chip, and it might need a sensor to read the position of the motor. And then lastly, you're going to want to do the full system. And depending on the complexity of your circuit board, this might not really be much. But a state machine in the end might be helpful to determine what subsystems do what at what time. So you can see that the steps kind of form a hierarchy here where you have peripherals that are used to interact with devices. Each device makes up subsystems, and then the subsystems are all controlled by the full system state machine. So now I gave you guys some general ideas about design, and we're going to talk a little bit about why those are applicable to this particular robot, which is Gucci. Gucci is a 3-kilogram autonomous sumo robot, which means that its job is to push another sumo robot out of the ring. And this robot can move at a speed of 2.8 meters per second, which is pretty fast considering its size, which is about 10 inches. And it'll have a 415 pounds of magnetic downforce because in order to win pushing matches, you need to be close to the ground. So the drivetrain is made out of these 70-watt max power, 72-amp stall current brushed motors that you can see here. And the motor controller selected is the RoboClaw 60 amps. And the 60 amps is the continuous current with 100 amps of peak current, which is good because the 100 amps exceeds the 72 amps of stall current, which is the maximum current that the motor can draw. And this motor controller communicates using a TTL serial protocol, which is a UART protocol type thing. Uses TTL means it uses 0 volts to 5 volts. And there's a variety of sensors on this robot in order to detect the ring and the enemies. The LiDARs are the time of flight sensors. They measure the distance to an opponent and they communicate through UART. There are line sensors, which have an analog voltage output, which is based on the light intensity. Later on, these get turned into a digital signal using a comparator, which basically checks to see if the output or if the input voltage is greater or below a certain threshold, and then turns that into a yes or no binary signal. There's a start module which tells it tells the robot when to go. Another radio which the team uses for debugging and basically monitoring, and then IMU, inertial measurement unit, which can detect the contact with the opponent. And IMU basically has accelerometer, so it senses the accelerations on the circuit and thus can calculate what the forces are. So we're going to talk about one particular design decision, which was choosing the time of flight sensor. Our two choices was TF Mini Plus, which is the current sensor used on the robot, and the VL53LOX, which was used on the previous version. So you can see that there are some particular advantages, such as range, the field of view being smaller, which is good because these sensors don't detect unless the entire field of view is eliminated. So the farther away you get, the bigger that cone gets. And the VL53LOX, with its 25-degree field of view, means that when you're at the distance of the ring, which is about 1.5 meters, the opposing robot's not going to cause the sensor to trigger, so it's not going to detect. And another key aspect here is that the refresh rate is up to 1 kilohertz. Since these robots move fast, you need your sensors to move even faster to keep up. And so having a high refresh rate sensor is better. And of course, there's some drawbacks though, because this is far more expensive and far bigger than the alternative. So now we're going to talk about the microcontroller. For Robo Wrestling, there's no PC and there's no ROS running, so the microcontroller does 100% of the work involved in processing and decision making. The Teensy 3.6 was selected because it has very easy Arduino IDE and library support. There are a lot of custom libraries and built-in libraries for the Teensy, which makes it very effective. It has a lot of pins, and at a point in time, it was one of the fastest clock speed microcontroller boards with the hobbyist-like package for development. And then one con was that the pins aren't all 5-volt tolerant, and 5-volt is pretty much the most common voltage for components to run at. You more often than not, you find 3.3, and it's getting more trendy to use 3.3, but 5-volt is pretty common. So here, once again, we're going to try to make a comparison of the Teensy 3.6 to an alternative microcontroller, such as the Pro Micro. One key difference is the processor type between the Teensy 3.6 and the Pro Micro. The Teensy uses an ARM Cortex M4 microcontroller from the company called NXP, whereas the Pro Micro uses an AVR ATmega32U4. And you might not know right now what the difference between AVR and ARM are, but it's very important to know that ARM is a more advanced processor design, which has some notable advantages which allow it to support more RAM, different features such as floating point unit, and more interrupts. And you can see that these are reflected in the Teensy's specs, where it has almost 100 times more RAM than the Arduino Micro. It has twice as many pins, and it has 44 interrupts compared to the 6 of the Pro Micro. And those features are pretty much based on how that ARM processor architecture versus the AVR processor. The operating voltage is 5. It means you can power it with a 5-volt regulator, but the 3.3 volts is all you'll get from the pins. And this also has far more different communication ports compared to the Pro Micro. And part of that is due to the fact that it just has more pins. You have more room to break out your different communication signals. So with these things in mind, we can now look at the block diagram for Gucci, and your future projects or currently working on projects, you should definitely consider making a block diagram so that you know what features you're going to need and how to organize them. But you can see it's all powered from a battery, which has a power control circuit. This is a new board which just has voltage regulation and monitoring built into it. The power control splits off the power from the battery into the 2 ESCs and then the 2 motors. And in the middle, you have the main PCB, which contains the microcontroller, multiplexers, comparators, IMU, and radio. So the comparators here take the line sensor input and turn it from an analog signal into a digital signal. And the multiplexers are used to allow you to split one communication bus into many. Because there are 6 LiDARs, that's more than the number of UART ports, and 2 UART ports are already occupied for communicating with the ESCs. So this board, as you know, there's a lot of different components on it. This board layout is pretty dense. There's components pretty much everywhere, but we can talk about it in stages. So as I mentioned before, there's LiDARs, and those LiDARs form plugs which go around the perimeter of the board. You can see them here. There's just all the plugs and some pull-up resistors. And as I mentioned before, there's multiplexers, which allow the 6 different LiDARs to run off of one single communication bus. And as long as you communicate with each LiDAR one at a time, you can use the multiplexer to select that one. Here are the line sensors. The line sensors are those 2 large 2x2 connectors that you can see, or multiple large 2x2s that you can see here, here, here. And here's the comparator. It's a dual comparator, which means that there's 2 of those circuits in one chip, and they allow you to turn the line signals or the line sensors analog output into a digital output here. And one key feature that I think is pretty interesting of this board is that the line sensor reference voltage can actually be selected by the microcontroller. And the way that these comparators work is that if the positive input is greater than the negative input, the output goes to the positive voltage. If the positive is less than the negative, it goes to 0. So that's how you get your digital signal 1, 0 out of an analog signal. And we can choose in the code where that threshold is, which allows us to kind of tune the sensitivity. And here's the IMU, the inertial measurement unit. As I mentioned before, sometimes you might have problems with communicating between devices at different operating voltages. Here's an example of that. The IMU only operates at 1.8 volts, which is really common for low power devices for IoT or others. But the Teensy runs at 3.3. And if the Teensy just tried to talk to this directly, it would just blow up those pins. So in between the two, you have to add this, which is the level shifter chip. And the level shifter just takes 3.3 volts and duplicates the same signal at 1.8. For I2C, you have to get a special I2C level shifter, which is why these are labeled with the I2C pins. And lastly, you have the Teensy. A lot of functions on this board, and you can see that pretty much every pin on the Teensy is being used. Your size of your board, you should try to choose a microcontroller which has just as many pins as you need so that you can avoid making your circuit unnecessarily big. So there's a question. What does the level shifter do? So you can see that the IMU is 1.8 volts circuit, or is a 1.8 volt device. And the Teensy's digital I/O pins are going to either be at 0 or 3.3. So you remember that since I2C is a digital protocol, there's only going to be 1s and 0s coming out, which means the voltage is either 0 or 3.3. So the level shifter takes inputs that are at 3.3, which you can see here, and turns them into 1.8 volt signals on this side. So that way you're not going to blow up the pins of a 1.8 volt device by giving it more than its allowed voltage. Did that answer the question? Cool. Thank you. And if you guys have any more questions, feel free to put them in the chat. So yeah, lastly, to kind of show the same structure, we have for the firmware of the Gucci system, you have different peripherals such as UART, SPI, I2C, and digital I/O. And these different peripherals can be used for different functions, such as the UART is used for both the ESC and the time of flight sensor, which necessitates the use of the multiplexers as mentioned before. The radio communicates with SPI, the IMU communicates with I2C, and the line sensor just uses digital and analog IOs, very basic. And then you can group all of these different subsystems of the robot into the different groups: control, perception, diagnostics. And control will use the motors. You're trying to get the robot to move. Perception, it's going to more importantly use the sensor data, such as the time of flight sensor, the line sensor, to get an idea of what the robot is doing and where it is. And then lastly, diagnostics needs to take in information from all of them because it's used for debugging. So here's an example of the state machine of what Gucci uses for its behaviors. Here's the entry point, and then it'll start up and then follow this pathway of looking for the boundary, trying to turn towards the robot, or trying to push the robot, and then reacting to the lines, which is this following branch here. So in a nutshell, it's very important to plan out your designs. That's why we put so much emphasis on the component spec and block diagrams and requirements. If you go in and try to draw your circuit schematic right away, you're going to get lost very quickly thinking about, oh, why do I need this level of component? Why do I need that level of component? And in doing so, you'll either make your design unnecessarily complicated, unnecessarily large, or unnecessarily expensive. It's important to collaborate with other sub-teams, as mentioned, for choosing motors and sensors. And it's also important to understand the context of your board in the overall system. And lastly, just like how in CS there's a concept of object-oriented programming where you break things down into different levels, you can do the same thing in your electrical and even your firmware, where you have each of your individual sub-circuits kind of acts on its own, but then has some links to a bigger picture. So that's about it. Thank you guys for listening, and that was the last presentation of electrical training. So there's going to be a form posted in the chat. We would really appreciate some feedback from you guys. I know that this is the first week or first year that we've done online electrical training, so it's a big change. And even beyond that, we've made some new content this year, and we really hope to get some information from you guys about what you think was good or what you think was bad about it, so we can learn more for the future. So I'm going to, or someone's going to copy and paste that. It's already been done into the chat, but yeah, that's it. Thank you guys for listening to me, and good luck with the rest of your projects in RoboJackets and in life, I suppose.